Hello everyone, and welcome to the Unit 1 of this course, Introduction to Programming or Programming in C. The title exactly doesn't matter, so I'm sort of using a few closely related but slightly distinct titles in relation to this course. The primary idea of the course is to introduce you to programming from the context of understanding how the computer works and how to exactly make use of the facilities provided by the computer. Now, some of you may already be familiar with other programming languages such as Python or Java or maybe even C itself. My goal in this course is sort of to explain to you why C is a useful language, especially when we want to understand exactly how a computer works, which, at least from the point of view of a student of electronic systems and also for a student of computer engineering at least, and possibly also for a student of computer science, is quite useful, because at the end of the day, knowing how exactly a computer works makes a big difference to how you are able to make use of it. So this is Unit 1, and in this I am primarily planning to cover the topic of how a computer works. So an outline of the topics that would be covered in this unit, which is essentially roughly covering 1 week worth of class, is we start off by trying to understand what is a computer, right? And what I mean by that is, what is it made of? How do the different parts of the computer interact with each other? So that will be a fairly significant chunk of what we are going to look at in this unit, and it will sort of naturally lead us to the next topic, which says what is programming, right? How do we get a computer to do what we want or what we expect it to do, right? There has to be some goal in mind, and finally what we want to do is to see how do we get the computer to achieve that goal for us. And along the way, I hope to impress upon you why C in particular is a very useful language in order to understand how a computer works, and also to help us get the best out of what the computer can do. Okay, and along the way as we proceed, I will be sort of trying to essentially compare and contrast the C programming language with various other languages that you might already be familiar with, or you might have heard of, or you will probably be learning as you proceed, right? C sort of holds a unique position in that regard, in the sense that it has its roots very close to the basic nature of what a computer is, and in that sense, in order to really get the best performance or the best effect out of what we want to do with the C programming language, it means we also need to learn a little bit about how a computer works. So with that, let's get to the first topic over here, the computer. What do I mean by this? What I am trying to convey over here is, we want to sort of build up slowly the basic concept of how a computer is constructed. And when I say a computer, I don't mean the big black box that's sitting on your desktop, or even the laptop that you carry around. The computer that we have in mind over here is one very specific chip that is present inside these devices, right? Normally it would be normally called the CPU, the central processing unit. Now a number of people sort of refer to that big black box itself as the CPU. It's not, right? The box is the computer, it has the CPU, and it has a lot more than the CPU itself. What I'm going to be doing over here is to try and motivate how a chip like the CPU might work, how it is designed, and what we need to understand about it in order to really make good use of it. So let's start with a very basic concept. First things first, the word computer itself, right? The word computer naturally is associated with this idea of performing computations. Okay, so as an example of a computation, I'm going to take a very simple task. I want to add two numbers together, okay? And this is actually a good piece of sort of history to keep in mind, right? Why were these devices even called computers? Because their primary goal was precisely to aid with computation, right? The biggest sort of motivating factor for these devices was somewhere during or around the Second World War, when a large number of computations needed to be performed in order to do missile guidance, in order to do nuclear physics simulations, and various other kinds of things, where normally those would have been done by hand by people, right? And quite literally those people were called computers because their job was to assist with performing computations. The goal of the entire sort of theory and the machines that were being built at that time was to see how could we do those jobs faster, right? And the focus was entirely on computation at that time. So in our case, we are going to start with a very simple task: add two numbers together. So there are a few things that we need to assume over here and a few other things that we will need to sort of point out, right? One thing that you need to keep in mind over here is I am trying as far as possible to almost like build this up from first principles, so to say, but in practice that's nearly impossible because everyone has some kind of natural idea of what a computer is, what a computer does, what a number is, and various other kinds of things. And it's quite possible that I also have my own hidden preconceptions of what is obvious and what is not. So there may be instances over here where I sort of say, oh, store a number in a certain place, right? And it won't be obvious how exactly we do that in a digital circuit. My goal over here is as far as possible to try and identify those things which are not obvious and give a very high level hand wavy kind of explanation of how it could be done, right? But the fact of the matter is that in order to fully understand how a computer works, you then need to start digging deep into digital logic and the theory of computer design, okay? So there may be several instances over here where when I say, for example, oh, you store a number in this memory location, right? So some terms like that may not be entirely obvious, you sort of take it at face value. You assume that a number is an object, and by object I don't mean the object is in object oriented programming, let's not confuse things further over there. I just mean a number is a thing that can somehow be stored or kept safe, right? The fact that a number then needs to be converted into electrical voltages or currents or charges, right, and stored somewhere on a capacitance or in some wires or in some kind of a feedback loop inside between two transistors, all that is not really relevant for us, right? We will assume, first of all, that numbers can be represented, right? So that word represented, there's a reason I'm highlighting it over here, because it is something that we will start looking into in a lot more detail at a later point. Because how exactly do we represent numbers inside a computer actually plays a significant role in what computers can do. Okay, so for now I will just assume that numbers can be represented as electrical signals. Okay, why electrical signals? Because as of now we know that computers can be built out of electrical circuits, right? How exactly do you build computers out of electrical circuits? Out of scope of this particular course, but very much within the scope of a course like, let's say, digital logic or digital system design, right? We also assume that we have a circuit that can add such signals, right? Now at this point all that we know is, all of us know how to add two numbers. We know, for example, that 2 plus 2 is equal to 3, 3 plus 5 is equal to 8, and so on, right? How do we do that? There are standard rules that we have learned. A computer doesn't follow exactly the same kind of rules. In the first place, the representation it uses internally is not the decimal representation that we are used to. Once again, like I said, we will look at that a little bit more later, right, in another video. But for now, what I'm going to assume is, there is a circuit, there are numbers that can be represented as electrical signals. If I connect those signals as the input to that circuit, the output of that circuit will basically be something that represents the sum of those two signals, okay? So this, like I said, is an assumption at this point, but practical experience, we know that there exist such things, okay? So what I have over here is what would normally be called a schematic representation, right? So what I've got is this circle with a plus inside it is some kind of a schematic representation of this adder circuit, right? So essentially what it's saying is it takes two inputs which I have connected through A and B, right? So these two values over here, there's this A and there's this B, and I have just drawn them with arrows right now, right? But the fact of the matter is, in reality, those would actually be physical wires that are connected somewhere in a circuit. Those two go into this adder, the adder does something, and out comes S, which is the sum of these two values, okay? So we assume that the circuit has been built appropriately, right? It works the way that we expect it to. All right. Now, where do we go from there? A little bit of terminology, right? In this diagram that I have over here, A and B are usually called the operands, okay? They are the two input values, so to say, that are being operated upon, right? Some kind of operation is being performed upon them, and in this case the operation is addition, right? The plus sign indicates the addition. So there is an operation, right? When I say operation, some kind of function, some kind of work is being performed, right? The two operands A and B are the inputs to that operation, and S is the result of the operation, okay? So the reason why I am sort of trying to highlight these is there is a lot of jargon that sort of implicitly gets carried along when we use the terminology of how computers are built and how they work, right? So I'm hoping that at least at some point I have some kind of a point of reference that you can go back to and look at and say, okay, these are the terms. Most likely you are already familiar with them. If not, they are fairly, in most cases, fairly commonsensical, right? And in other cases, there should be some way by which you can refer to them and figure out what the meanings are. So in order to perform this operation of addition, right, there are a few requirements, right? Like I said, we need to be able to represent the numbers as electrical signals, okay? And this, to a large extent, is what the theory of digital systems is all about, right? And for those of you who have already done a course in that area, you would be familiar with the term bit, right, which is basically a short form for binary digit. And ultimately, everything that is stored inside a computer is in the form of bits, zeros and ones, as we say, right? How exactly do bits get represented? How are they used? What do we do with them? Out of scope of what we are looking at right now, but very relevant. I mean, in the sense that at least the concept of a bit and how they get used inside a computer is something that we will need to be spending a lot more time on, right? We will look back at it again later when we talk about data representation. Once again, we also need to have hardware that is capable of performing the operations that we want. And once again, that is in the realm of digital logic, right? So digital logic circuits are precisely meant for this purpose in order to be able to perform these computations. And one other thing which may seem obvious but actually turns out to be non-trivial for computers is how do we communicate with the outside world, okay? In the example that I showed you, the communication essentially consists of where do I get A and B from and where do I send S to, right? So A and B are the inputs, S is the result. Where do I get A and B from and where do I send S, okay? Now at the end of the day, what is happening is that physically these are all going to be implemented using some kinds of wires, right? So there will be some wire that takes in the input A, another set of wires that brings in the input B, perform the computation internally, and some other wires that take the result S and carry it out somewhere, okay? Where, how, we will look at later. So far so good. At this point, what I have assumed is that we have a piece of hardware that is capable of performing the addition of two numbers. What if I don't want to just add two numbers alone? I have two sequences of numbers A1, A2, A3, A4 and so on, and another sequence B1, B2, B3, B4 and so on, and I want to add pairwise, okay? So I want to get the result S1 is equal to A1 plus B1, S2 is equal to A2 plus B2 and so on, right? So can I use the same hardware in order to do that, right? So that becomes the question. And well, it seems reasonable enough, right? What it looks like I need to do is I can use the same hardware in order to perform my computation, but now I need somewhere where I can store my input values, one set of values for A another set of values for B, and have some kind of a hardware or some kind of mechanism by which at different instants of time I can get different values of A and B out. Okay. So one way of looking at it could be that maybe I have a counter or somebody, a gatekeeper, who basically says A, that rectangle A, give out the first value. Similarly, at the same time, rectangle B, give out the first value. And the moment both those values are connected upon the wires, this circle out here does its job, which is just adding the numbers together. What does it do with the output? That goes into another box out here, okay, where the S values get stored or saved. Okay. So these blocks that we have over here, right, these rectangle blocks that I have, I'm going to refer to them as memory. Okay. And this concept of memory is very important. Right now, all that I care about is it's a place where I can store some information, right? And what I'm assuming over here is all the A values are stored in some kind of memory, all the B values are stored in some other kind of memory, and the results, once I obtain them, are also stored into another kind of memory, right? So what does it mean? There are some functions that I expect of the memory, right? One way to look at this memory is that it's just a bag into which I can put things, right? And that operation of putting something into the bag I refer to by the term write. Okay. So when I put something into that bag, I say I have written data into the memory. I also might want to take something out of the bag, and I say that when I want to get something out of the bag, I am reading something which was in the memory, right? Both of these seem simple and obvious enough, but for it to be useful, there has to be some way to identify where in the bag did I keep this, right? So maybe a bag is not the most sort of the best possible concept in order to understand what a memory is. It might be better to think in terms of, let's say, a desk where there are, or a filing cabinet, right? Where I have some way of specifically identifying, okay, what was on the third row and the fourth column inside that filing cabinet, okay? That information, where exactly was something stored, is what we call the address, right? Once again, the reason I am highlighting these is because these are terms that we will be using repeatedly in the context of how the computer works. What I am describing right now is just a very high level analogy that could hopefully help you to understand it, but you always need to keep in mind that the memory is not physically a bag, right? And there are places where the analogy breaks down. For example, a bag can expand, right, whereas memory has a very specific capacity, right? A bag can sort of take things in different shapes and put them together. Memory has restrictions on that. So at best, what you should probably be trying to do as you go forward over here is try and form your own kind of analogies for what the function of a memory is, right? This is sort of a starting point. It tells you one way of looking at it, but at the end of the day, you need to sort of see, okay, how exactly do I build upon this? How do I get a better understanding of what is happening in here, right? But the key thing from our point of view is I have the ability to write something into memory, and I have the ability to read out those values later. And there is something called an address that tells me where exactly in the memory I put something so that I can retrieve it later, right? It's sort of a tag, for example. And one way of looking at it might be that when you go into a shop and if you're already carrying a bag with you, sometimes you are asked to leave it at the entrance, and the guard might give you a token saying when you leave you can present this token and get it back. What does the guard do? They take the bag and keep it in a secure place which also has a copy of the token. And when you come back with your token, they match it with the token that's been kept over there, take out your information or your bag, right, or your whatever it was that you kept for safekeeping, and give it back to you. A similar kind of thing has obviously got to be implemented using some kind of electronic circuitry in hardware, right? As far as we are concerned, we are abstracting it out and saying we want to be able to write to a particular address and then read back that value later from that address. So in practice, this concept of word, right, is something that we will be repeatedly encountering as we proceed through the language, right. It's a slightly confusing term, right, because we usually use word to mean a word in English, whereas over here a word is actually either a number, right, or a very specific set of bits, right. At the end of the day, as far as the memory of a computer is concerned, a word may not have any actual English meaning or a meaning in any other language. All it means is a collection of bits that occupies some space in the memory of the computer. Okay. So in practice, what happens is that we are interested in these words, and each word has something that we call the width, the data width of that word. Okay. Once again, like I said, later on when we talk about data representation, we will be interested in finding out what exactly is this relationship between the data width and how a computer works. The other thing that is important to keep in mind as far as memory is concerned is there are typically a finite number of addresses. There is a finite amount of space in the memory, right? And this is usually called the capacity of that memory. So both of those are terms that when you talk about the memory and how it is going to be used, you need to keep it in mind.